Hello. In just recent sections, we had gone through developing confidence intervals to give a range of values for where we think a population mean or population proportion might be. In the upcoming sections, we're going to be developing really the meat of statistics that is used in the real world, and that's known as hypothesis tests to determine the validity of claims that are made. And so we kind of develop it just a little piece at a time. Today we're going to be working on stating hypotheses and the type of errors that occur and what we're trying to avoid when we develop these, what we're calling hypothesis tests. So we'll get to that here in a moment. Let's just to talk about this lead-in situation. So in the upcoming sections, we're going to continue with our investigation of inferential statistics, making inferences based on the statistics that are provided. But now, instead of making an estimate about a population parameter, we're going to be learning how to test a claim about that parameter. So for an example, let's say an automobile manufacturer advertises that its new hybrid car has an average mileage of 50 miles per gallon. To test this claim, we're going to take a sample. If the sample mean is different enough from that advertised mean, then we're going to decide whether that advertisement is false. And we're going to decide on it being true or false based on how likely it was that we obtained that value if the true average really was 50. To fully understand this idea, we're going to read page 348 out of our current book, starting with the paragraph, "For instance, consider." So if you want to follow along with your book, it's on page 348. Otherwise, I'm just going to read it right now. Here's the idea, and it's important. You might want to read this 2 or 3 times and really take it slow to understand the concept. Same thing I just said a second ago. New hybrid car, average mileage 50 miles per gallon. You suspect the mean mileage is not 50 miles per gallon. So how could we show that the advertisement is false? Obviously, we cannot test all their vehicles, but you can still make a reasonable decision about the average gas mileage by taking a random sample from that population of vehicles and measuring the mileage of each in that sample. If the sample average differs enough from the advertisement's average, we can decide that the advertisement's average maybe is false. So for instance, to test the mean mileage of all hybrid vehicles of this type, assuming that the average is 50 as they're advertising, we take a random sample of 30 vehicles and measure the mileage of each. We obtain a sample average, and that sample average is 47 miles per gallon, and our samples deviate with a sample standard deviation of 5.5 miles per gallon. Does this indicate that the manufacturer's advertisement is false? Well, to decide, you need to do something unusual. We have to assume the advertisement is correct. So what we're going to do is we're going to assume that they're not lying, that the true average really is 50. Then what we're going to do is we're going to examine the sampling distribution of sample means under the central limit theorem, taken from a population in which the mean really is 50 and our standard deviation is 5.5. From the central limit theorem, we know the sampling distribution is normal with a mean of 50, and our standard error is the standard deviation divided by the square root of 30, which turns out to be 1. In the figure below, notice that the sample mean of 47 miles per gallon is highly unlikely. It's about 3 standard errors from the claimed mean. Using the techniques we studied in Chapter 5, we can determine that if the advertisement is true, that the value of the population's mean really is 50, then the probability of obtaining a sample mean of 47 or less is only about 0.0013. That's highly unusual. That means there's only a 0.1% chance that we would have even gotten that sample of 30 to have an average of 47. Our assumption that the company's advertisement is correct has led us to a very unlikely event. So there's either 2 options. We either had a very unusual sample or the advertisement is probably false. The most logical conclusion is that the advertisement is probably false. The more likely conclusion is that the true population's mean is probably somewhere around 47. It's highly unlikely that the real average is 50 and we just observed a very unusual event. That's what we're going to be working towards. We're going to be conducting what's called a hypothesis test, which is kind of what we just generally described a second ago. A hypothesis test is a process that uses a sample statistic to test a claim about the value of a population parameter. The statistical hypothesis is a statement or claim about a population parameter. You need to carefully state a pair of hypotheses, one that represents the claim and the other represents the complement. When one of these hypotheses is false, the only option is that the other must be true. There's only two possibilities. The two types of hypotheses are going to be what's called the null hypothesis and the alternative hypothesis. The null hypothesis is that a statistical hypothesis that contains a statement of equality, such as less than or equal to, or greater than equal to. We denote it H for hypotheses with a 0 as a subscript. It's either read as H0, HO, or H0. It's really the null hypothesis. The reason it's called the null hypothesis is because we are testing the claim that it is not different from the original. Not different meaning zero difference. The alternative hypothesis is that the null is false. It would be the exact opposite claim. The alternative hypothesis is always the claim that has the inequality statement, such as greater than, not equal to, or less than. If the null is false, then the alternative must be true, and we read it as HA or alternative hypothesis. These are complementary events. They cannot both be true. If one is false, the other has to be true. Note, the null must always contain the equality. This is because the null, which comes from the phrase nil or zero, implies zero change. If there is no difference between the statement and the finding, then there is zero change. We have no reason to believe that they were lying because there's zero difference or not enough of a difference. When stating a hypothesis, that is to write the null and alternative hypotheses, you translate the claim made about the population parameter from a verbal statement to a mathematical statement. Then you write the complement. So if our null is that the mean is less than or equal to some value, the alternative would be opposite, would be greater than. If the null is that the mean is greater than or equal to some value, the opposite would be that the mean is less than some value. If the null is that the mean is equal to some value, the opposite of equal to is not equal to, so the alternative would be that the mean is not equal to some value. Regardless of which pair of hypotheses you use, you always assume that the mean is equal to some value and examine the sampling distribution, that is, the values that we obtain from our sample, on the basis that the assumption is true. We are always testing the assumption is true. I'm going to make the analogy here that is very common that our legal system is based on, is we assume that someone is innocent, and then it is our job to prove that they are guilty. So that the null is always the assumption that something is true. We believe it's true until we have enough evidence to say that that's highly unlikely that it is actually true. Type of questions that are in this section are just getting you used to writing the two hypotheses. So write the claim as a mathematical sentence, state what the null is and the alternative, and identify which one represents the claim. So a company claims that 61% of its appliances will be repair-free in the first decade. Well, in this case, the null claim is that the proportion is equal to 0.61, 61%. The opposite of equal to is not equal to. So alternative would be that it's not equal to 0.61, and the claim is this one. That's what they claim, that it is equal to 0.61. The second statement, a car dealership advertises that the average time for an oil change is less than 15 minutes. The null always needs to contain the equality. So in this case, the null would be that the mean is greater than or equal to 15. The actual claim is the alternative, because the alternative is the one that doesn't have any inequality, doesn't have any equality statement. So the alternative is actually the claim in this case. Be aware, though, this is where I disagree a little bit with the book. Almost always, we are always going to be testing when the claim is the null. It's most of the time, it's highly unlikely that we're ever going to be doing a hypothesis test where the claim is the alternative. Almost always the claim has some type of equality statement in it. But we're just practicing right now. In this case, the claim is the alternative because the claim was less than 15 minutes. And the statement less than doesn't have a less than or equal to, so it must be the alternative. Last one, a hose company claims that the average flow rate is more than 18 gallons per minute. More than, again, would be a statement of the alternative because it doesn't say 18 or more, it just says more than. So the alternative would be average is greater than 18. The opposite of that is less than or equal to, so the mean is less than or equal to 18. In this case, the claim is with the null, or is with the alternative hypothesis, which is going to be not the standard case when we actually make these tests later. But when we're just practicing right now, it could occur, I guess. I'll give you a chance to try. So your task is to write the claim as a mathematical sentence, state the null and alternative hypotheses, and identify which represents the claim. First one is Consumer Report claims the average lifetime for a car battery is not 74 months. And the second one is a realtor publishes that the proportion of homeowners who feel their home is too small for their families is at least 24%. So pause the video now, give yourself a chance to try. Here we go, the first one. The claim was not 74, that's the alternative. So the null would have to be it is 74 months. The claim in this case is the alternative. And the second one, the claim was that it is at least 24%. That means 24% or more, so that has an equality statement with it, so it must be the null. The alternative is less than 24. And that is how we define the two hypotheses based on the stated claim. No matter which hypothesis represents the claim, we always begin the hypothesis test assuming that the equality condition in the null hypothesis is true, just like I've said prior. At the end of the test, we have two decisions. We either are going to reject the null hypothesis. That means we have the event we actually obtained was so unusual that we probably don't believe the null is true, so we would reject it. So that's option number one. Or maybe the event that we got matches up very nicely with the null statement, so then we would say we fail to reject. There isn't enough evidence to say that the null is not true, so we fail to reject it. Because your decision is based on a sample, there is the possibility of making the wrong decision. We could maybe reject the null when it was actually true, or we could fail to reject the null even though it was false. Because of random error, those things can happen. This is a really important idea, so we're going to read a thought experiment discussed on page 351. So again, please follow along in your book. It begins with a paragraph, for instance, you claim. For instance, you claim that a coin is not fair. To test your claim, you toss the coin 100 times, and you get 49 heads and 51 tails. You would probably agree that you do not have enough evidence to support your claim. Even so, it is possible that the coin is actually not fair and you had an unusual sample. But then you toss the coin 100 times and get 21 heads and 79 tails. It would be a rare occurrence to only get 21 heads out of 100 tosses with a fair coin. So you probably have enough evidence to support your claim that the coin is not fair. However, you can never be 100% sure. It is possible the coin truly is fair and we just observed a highly unusual sample. So let P represent the proportion of heads. The claim that the coin is not fair can be written as the mathematical statement P does not equal 0.5. Its opposite or complement is that the coin is fair, and that would be that the proportion is equal to 0.5. So our null hypothesis and alternative are the null is that the coin is fair. It's equal to 50% success rate, and the second is that the coin is not fair, and the percent is not equal to 50%. Remember that the only way to be absolutely certain of whether the null is true or false is to test the entire population. Because your decision to either reject the null or fail to reject the null is based on a sample, you must accept the fact that your decision might be incorrect. You might reject a null when it is actually true, or you might fail to reject a null when it is actually false. These types of errors are summarized in the next definition. Since there are two types of errors, well, they were very creative with their name and they called them type 1 error and type 2 error. Type 1 error occurs if the null hypothesis is rejected when it was actually true. Type 2 error occurs if we do not reject the null hypothesis, that is, we fail to reject it when it was actually false. So the two types are shown right here. There are four things that can happen. The null is true and we do not reject it. That's a good decision, right? Or maybe the null is false and we actually do reject it. That's good. But we could make errors. Maybe the null is actually true and we reject it. We call that type 1 error. Or maybe the null is actually false, but we fail to reject it and we didn't necessarily do the job that we were intending to do, so that would be type 2 error. Type 1 error occurs if the null is rejected when it was true. Type 2 error is the null is not rejected when it was actually false. Hypothesis testing is sometimes compared to the legal system used in the United States. I referenced this earlier. Under this system, the steps are used. First one, a carefully worded accusation is written. Step two, the defendant is assumed innocent until proven guilty. That is, we assume the null. The burden of proof lies with the prosecution. If the evidence is not strong enough, then there is no conviction. A not guilty verdict does not prove that a defendant is innocent. That's important. You will never hear in a court case that someone is claimed to be innocent. We only say not guilty. That is, in statistics, we would say fail to reject. We can never say that the null is true. We don't have enough information to say that it's true unless we sample the entire population. The evidence needs to be conclusive beyond a reasonable doubt. That means we have highly unusual events. The system assumes that more harm is done by convicting the innocent, that is type 1 error, than by not convicting the guilty, type 2 error. So in our legal system, we do everything that we can to avoid type 1 error. So here's the analogy. Let's say that the verdict is innocent. Let's say that the verdict is innocent. We find not guilty, that would be justice. Let's say that they are guilty and we find them guilty, that would be justice as well. What would be bad is if they are truly innocent, but we find them guilty. That means we're putting an innocent person in jail, and we try to avoid that at all costs. That's why we assume innocent. Type 2 error would be that somebody is guilty, but we find them not guilty. So that would be we let a criminal back into society. We've decided that that is an error, obviously, but it is not as severe of an error because we are not punishing an innocent individual. So in our justice system, type 1 error we have decided is more egregious. But it really depends on the scenario. So here's a scenario where it could be different. The USDA limit for salmonella contamination for chicken is 0.2%. A meat inspector reports that the chicken produced by a company exceeds that limit. You perform a hypothesis test to determine whether the meat inspector's claim is true. When will a type 1 or type 2 error occur? Which one is more serious? So the first thing you need to do is write the two hypotheses. The first one is that the proportion is less than or equal to 0.002, that's 0.2%. The alternative is that it's greater than 0.002, which is greater than 0.2%. And that's the actual claim that was being made. Step 2 is to identify the two types of error. Type 1 error is rejecting the null when it is actually true. That would mean that the actual proportion of contaminated chicken is less than or equal to 0.02, but we decide to reject the null. Type 2 error is failing to reject the null when it is actually false. So that would mean the actual proportion of contaminated chicken is greater than 0.002, but we do not reject it. Step 3, interpret our results and determine the severity of each error. So with type 1 error, that would mean that we create a health scare and hurt the sales of chicken producers who are actually meeting the USDA limits. Because if we were committing type 1 error, we would be saying that there is actually more than 2% contaminated when there actually isn't. And so we would be punishing the company, but luckily nobody would be getting hurt. Type 2 error, though, would be probably worse in this scenario because we would be not finding enough evidence even though it should have been rejected. So that would mean that we allow chickens that exceed the limit to be sold to consumers. And type 2 error in this case is more serious because it could result in sickness or even death because we failed to reject something that really should have been rejected. And that is it for day 1. Most of it's just going to be analyzing scenarios like the one that we did, setting up the two hypotheses. Thank you very much.